look at this function and imagine x getting really big, and look first at the numerator and realize that as x gets big, x to the fourth is going to get bigger much faster than these lower power terms, so these lower power terms become insignificant by comparison. Apply the same reasoning to the denominator. The highest power term in the denominator dominates all of the others. The others become insignificant by comparison as x gets really big. So as x approaches infinity, or in other words, as x gets really large, the lower power terms become insignificant, and this function will behave like what you see remaining here after those other terms have been ignored. It will behave like x to the fourth over x squared. And that's really easy. X to the fourth over x squared simplifies to x squared. And we know what x squared looks like. We know that's a parabola opening up. And if you just know that graph, x squared, has a shape something like this, then you can see as x becomes big, the value of the function gets really huge, and as x becomes extreme in the negative direction, the value of the function becomes really huge. And you can go straight to this. The limit as x approaches positive infinity of f of x is positive infinity in this case, and the limit as x approaches negative infinity of f of x is also, in this case, positive infinity. And you can get that just by looking at the lead terms, because the lower power terms become insignificant. And that thought process can be really fast and efficient and useful, especially if you have a really difficult function to work with, like this next example.
So all I do for these, so maybe let's look at let's look at A here real quick. 5 over x squared minus 9. All I do is first I just set the denominator equal to 0 and solve that. You know, this is going to be the tedious part of finding vertical asymptotes, is, you know, depending on what's on the denominator, you may have to use different techniques. Here I just have linear equation, or linear functions and quadratics, so they won't be too bad. We could either factor this, or we could use the square root property. I could add 9 to both sides. I could take the square root of both sides, but remember, when I take the square root, I have to add on positive and negative. And if you take the square root of 9, well, that's simply going to give us positive and negative 3. And at this point, to me, these are kind of the potential vertical asymptotes. I have to check that if I plug these values of x in, I don't get 0 in the numerator. Well, there's not even any x's in the numerator here, so certainly I'm not going to get 0 on the top. So these would be my vertical asymptotes. We would have x equals 3 and x equals negative 3 as our vertical asymptotes. Okay, so in a different video too, I'm actually going to graph rational functions, so I don't want to get into the graphing here just yet, just talking about how you actually find them. Okay, so that takes care of A. Let's look at the next one. Again, pretty simple examples here, just trying to give you the idea of you know, what you need to do algebraically. So x minus 1 on top, x minus 4 on the bottom. So again, I set the bottom equal to 0, and then I have to solve that corresponding equation. Again, here this one's pretty easy, just a linear equation. So all we have to do is add 4 to both sides, and we'll get x equals 4. So again, that's kind of my potential vertical asymptote. Notice if I plug it back into the original function, if I evaluate g of 4, well, in the numerator we'll get 4 minus 1, which is 3. On the bottom we get 0. We get something non-zero over 0. That means that this line x equals 4 is a vertical asymptote. Okay.